All right, so today's screencast is going to be about polar and nonpolar bonds. At first, we're going to start talking about polar bonds. And a polar covalent bond will be a bond between two nonmetals in which the bonding electrons are more strongly attracted by one of the bonding atoms. This results in a difference in electronegativity between 0.4 and 1.7 and an unequal sharing of electrons between two atoms. So an example would be something like a carbon and a fluorine bond, where if you were to subtract their electronegativities, the value of their difference in electronegativity would be between 0.4 and 1.7. So this is describing a bond, not necessarily a polar molecule. You can have a polar bond within a polar molecule or a nonpolar molecule. Then we'll talk a little bit about nonpolar bonds. And a nonpolar covalent bond is a bond between two nonmetals in which the electrons are shared equally between the two bonding atoms. This is because there is little to no difference in electronegativity between the two atoms. So an example of something like this might be a bond between two nitrogens. I should even really just draw a single bond, where if you were to subtract their electronegativity values, they are either equal to 0 or less than 0.4. So again, this also represents a bond. You can think of a polar covalent bond kind of like two siblings that don't share very well. And you could think of a nonpolar covalent bond as two siblings that do share well. Maybe even twins when you have two nitrogens. Okay. And then this next section starts to talk about polarity in shapes, or the molecule itself as opposed to just a bond. A polar covalent bond will create an individual bond dipole. Essentially what a dipole is an arrow, we represent it as an arrow that points towards where the electrons are more interested in being, or towards the more electronegative element within a molecule. If all of the individual bond dipoles within a molecule cancel out as a result of symmetry, the molecule is said to be nonpolar. An example of that might be if you have a dipole going this way and a dipole going this way. They cancel out, so there's not really one side of the atom in which the electrons are more interested in being. When individual bond dipoles in a molecule do not cancel out, then you would end up with a polar molecule. So for example, if you have two bond dipoles that point in the same direction, the overall dipole would look like that, and one side of the molecule would like the electrons more, or the electrons would spend more of their time near a particular element within that molecule. According to this definition, there are two shapes that are always polar, and that is going to include any bent structure. That could be a 104 or a 120. And the reason for that is because if you look at the structure, you have lone pairs on the central atom. And as a result of that, you end up with bond dipoles that point towards the central atom. Those bond dipoles do not cancel out, so that results in a polar compound. Something similar happens with a trigonal pyramid. You have a lone pair of electrons on the central atom, which pulls the electrons or causes the electrons to spend more time on one side of the atom. So one of the tricks is to look for lone pairs on the central atom. Now, with some more complicated structures, you'll find that this rule does not always apply, but for the shapes that we've been looking at, this rule of thumb will be okay. So we did a couple of these in class, but I'm going to take a look at the few that we didn't look at in class. So one of them that we skipped over was CH4. Now we have to start by drawing the Lewis structure and then identifying the shape in order to identify polar or nonpolar. So I know that each carbon atom gets 4 valence electrons, and each hydrogen atom gets 1 valence electron, so we get a total of 8. Carbon's going to be my central atom. I'm going to evenly distribute my hydrogens all around the outside of the carbon, and this ends up being my final structure. With 4 bonded atoms, this will be tetrahedral. And as long as all of my bonded atoms are made of the same element, each of them is hydrogen, this is going to be a non-polar structure. Then, if we take a look at the next one, PCl3. Every phosphorus atom gets 5 valence electrons. Every chlorine atom gets 7 valence electrons, so we end up with a total of 26. Phosphorus is going to be our central atom. We'll load up our chlorines are on the outside. Then each chlorine needs to fill its octet. Once all your chlorines have their full octets, then you can check and make sure that you have the correct number of valence electrons. We have 24 in this structure here, so we can add 2 more to the central atom and we're finally done. Now we notice that we have 3 bonded atoms and 1 lone pair of electrons, so we get a trigonal pyramid structure. And with a trigonal pyramid structure, we know that it will always be polar due to the pair of electrons on the top. And then another example would be with SO3. Each sulfur atom gets 6 valence electrons. Each oxygen atom gets 6 electrons, so we end up with 24. Sulfur goes in the middle. Each oxygen gets a octet. And then we realize now at this point that we have the correct number of electrons, but we don't have an octet on sulfur, so we have to move some electrons around and turn them into a shared bond on sulfur. So now we can see that we have 3 bonded atoms and no lone pairs of electrons, so this is going to be a trigonal planar structure. And trigonal planar structures are going to be nonpolar unless one of the bonded atoms is a different element. But we have all of the same elements surrounding, so this is going to be a nonpolar structure. And that is it for our polarity examples. The next part of these notes that is really important is to identify what hydrogen bonding is. And the most important thing that you need to know is that hydrogen bonding is an intermolecular force that occurs when a hydrogen atom is bonded to a largely electronegative atom such as F, O, or N. So these are the Fon bonds. Or you could also think of them as hydrogen bonded to fluorine, hydrogen bonded to oxygen, hydrogen bonded to nitrogen. Those are examples of hydrogen bonds. So one thing that you should know is that an intermolecular force or attraction is an attraction between two separate molecules. In the past, and over the course of most of our unit, we've been talking about intramolecular bonding, which accounts for ionic bonding and covalent bonding. This is bonds within one single atom. Or molecule, really bonds within one molecule. So when we talk about this, basically what we end up seeing with hydrogen bonds, and we're going to use water as an example because this is the most famous hydrogen bond. If we have a couple of water molecules, if you just take a second to draw all of those out, what you'll notice is that you'll end up with a partially positive or partially negative part of your atom. So the atom with the greater electronegativity is partially negative, and the atom with the lower electronegativity is partially positive. So a partially positive portion of your atom is going to have an attraction to a partially negative part of your atom, and vice versa. If you have a partially negative part, it's going to be attracted to the partially positive part. As a result of this, you are going to have a pretty strong bond between two molecules. When you see me draw this or something that looks like this, that means partial. So lowercase delta. And basically what hydrogen does is it attracts two different molecules together and keeps things close. And that's what actually gives water a lot of its properties. So that is it for our lessons on polarity and hydrogen bonding. Best of luck with your studies.